In this video, we're going to take this equation that we wrote down for the standard addition, when we're changing the concentration as we're adding standard additions, and take this and write this in a form that we can use for a linear calibration curve, using some of these definitions that are off to the side that you could see in the previous video, but I've just reorganized this a little bit. But these definitions over here with our XF and SF. So let's go ahead and do some algebra. So that's mostly what's going to be involved here. But this will derive the version of the equation that we can use to do a fit, where we can find the slope of the line, and part of that slope will involve this xi variable. So let me get some fresh space here. This will take a little bit of writing to do. So our initial equation is that we know that the initial concentration of our unknown is divided by the final concentration, combining our unknown and standard that we've added for our standard addition. That ratio is equal to the ratio of the signals that we get from our two measurements. So let's do our substitution for these two values down here with our dilutions, because usually what we'll know is the concentration of standard that we start with. We'll know that concentration, so we'd rather write things in those terms. And we need to write everything in terms of xi, because that's the variable that we're trying to find. So we can substitute from the definitions that were in the previous video. So we'll have xi divided by xi. Let me write that consistently, the I on the outside. So again, xi being here the concentration in our initial solution, which is what we want. That's what we're interested in. And that'll be equal to the initial volume. Right, we need to multiply that initial concentration times the initial volume divided by the final volume to find the final concentration. That's our dilution factor. And then a similar thing for our standard, but our initial volume of standard is Vs, which is different than the volume that we started with our whole sample. Vs is going to be a much smaller value, but still divided by the final volume. And then on the right-hand side of the equation, we still have Ix and Is plus x. And so the goal of this is we want to reorganize this that'll give us an equation that we can write out that'll look like a line where xi is just in one of those terms. Okay, so step one is, since this is ratios, we can cross multiply to get two things that are equal to each other. So this will get a little bit messy, but we'll have xi times the signal that we get from both the standard plus the unknown is equal to everything in the denominator. So we have both of these more complicated expressions here. Concentration of standard initial times Vs over Vf. All right, so all of that times Ix. All right, and I didn't cover it up with my face up here in the corner. Okay, and now our goal here is we want to simplify this. So on the left-hand side of the equation, we'll keep that the same. That's already pretty simple. It's just two things multiplied by each other. And then we'll just distribute the Ix in both terms here on the right-hand side of the equation. So we have xi times v naught over vf times Ix plus si times vs over vf times Ix. Okay, so now we have multiple terms here. So we'd like to isolate xi, so we're going to go ahead and divide by xi on both sides. And that'll give xi just on the right-hand side of the equation. So on the left-hand side, these will just cancel. And on the right-hand side, we have an xi up here already. So that'll cancel in the first term, and in the second term, it'll end up in the denominator. This may not be obvious why we want to do this, but that's the form it'll be in the end. So if we simplify this, we'll have I times s plus x, or I of s plus x is equal to v naught over vf times Ix, because the xi cancels because we divided by it, plus this SI Vs over Vf times Ix, not S, divided by Xi. Okay, so doesn't really look like a linear equation quite yet, but let's continue on. So our next step is we'd like to simplify some of these volume terms. So let's now divide by V naught over Vf. The idea here is we want to cancel this V naught over Vf here, and it will also partially simplify with this Vs over Vf. Okay, so we'll get on the right hand side of the equation, pretty straightforward, we'll get I times S plus X times Vf over V naught. Since we're dividing by this fraction, it's the same as multiplying by the inverse of the fraction. Okay, and then our first term will be Ix, and then we just need to look at what's happening with this here. So we have Vs over Vf times Vf over V naught, because that's the same thing as dividing by Vf over V naught. So our Vf's are going to cancel, and we're going to get Vs over V naught. Okay, and then I'm going to write this in a little bit different form, but we'll have Ix over Xi. And let me be consistent. The I goes on the outside. All right, so I've combined these parts here and written those fractions together times Si, and then these volume terms cancel out to just Vs over V naught. Okay, and this is the final form of the equation that we want. So let's point out which parts of these are y equals mx plus b. Let's do this in blue. So this is our y. This is going to go on our y-axis here. The Ix plus x times Vf over V naught. Ix here, this is the intercept. This is b. Ix over xi, this is our slope. And then our x values are, we'll use rainbow color here, over here, x. So it'll be our standard addition, the concentration of our standard times Vs over V naught. Now we can use this for just one, right? If we have just one standard addition, we can use this equation just fine. But what this is most useful for is if we do a series of standard additions. And we'll talk about that in the next video.